On some projects, the flow of water from the source to the point of connection passes through pipe or valves or sometimes other system components that you can't identify. And when that's the case, you can use a flow test to determine the design capacity and the pressure available for sprinkler operation. And that provides you with an approximation of the flow available at varying pressures, or it can also be used to provide the pressure available at varying flow rates. Sometimes the design capacity requirement is set and you need to know the pressure available for that flow rate. Other times you may want to use a specific pressure combination and you need to know the flow available under those conditions. Either way, a flow test can help you determine those variables on small and medium-sized projects. For a flow test, you'd use a simple setup like this with a pressure gauge, a valve to control flow, and some kind of bucket or other catchment container, along with a watch or a timer to determine how long it takes to fill the bucket or the container. Now, with a flow test, you may need to establish desired sprinkler operating pressure, maybe because you have chosen specific heads to use, or maybe to match existing heads that are being used elsewhere on the site. But once you've established what that operating pressure needs to be, you can make a calculation to determine the pressure needed at the point of connection to provide that operating pressure at the highest head. After the required pressure at the point of connection is established, the flow test apparatus can be attached to the point of connection, and then the valve can be adjusted until the desired pressure is met. Once that pressure is met, the catchment container can be placed under the water discharge point, and then the time it takes to fill the container is timed in seconds. And then that time is used for further calculations to calculate flow rate, which then becomes the system design capacity. So having said all that, let's work through an example. In this case, we've got a desired sprinkler operating pressure because for whatever reason, we want to operate sprinklers at 30 psi. So we have that information. We have an elevation change of 8 feet. We're using a 5-gallon bucket, and it takes 24 seconds to fill that bucket. So the question is, what is the pressure needed at the point of connection to deliver 30 psi to the worst case head? And then what is the design capacity? Now, unfortunately, we don't have an Excel spreadsheet in this case that does the calculations for us, but the calculations are fairly simple and they're written out on this particular worksheet. This is just to give you an example, but I like this worksheet. It's got all the information. You could easily set something up like this for yourself. And I'm going to talk you through it using our example information. So line 1 asks for the container size, line 2 the sprinkler operating pressure, which we already said we wanted to be 30 psi. We also had the elevation change information of 8 feet. We had pressure change due to elevation, or we will have it. We will also have pressure required on the gauge, and we know the time it took to fill the container, and we will also determine design capacity at the desired operating pressure. So some of this information was given to us in the example, but there are some calculations, of course. In line 4, the pressure change due to elevation is determined, and that's calculated just the same way we've been doing it all along. So taking our elevation change, multiplying it by our constant, ending up with a change of 3.46 psi. The next calculation takes the desired 30 psi and divides it by another constant of 0.67. What this constant does is it accounts for pressure loss from the point of connection to the last head due to friction, loss through pipe and valves and so on. That pressure is then adjusted for elevation change, which we've already made that calculation, and that's going to be adjusted either up or down depending on whether the point of connection is below or above the highest head on the system. Finally, well, not finally, but once that is done, you end up with a pressure required on the pressure gauge. So you would use the valve and adjust it until the pressure gauge reads approximately 48 psi, and that's where this number comes from. Okay. Finally, the design capacity at the desired operating pressure is calculated by multiplying the container size by 60, that's just the number of seconds in a minute, and then dividing that number by the time it took to fill the container, which in this case was 24 seconds. So once you multiply that all through and cancel out the units, you end up with 12.5 gallons per minute. So the design capacity at that desired sprinkler operating pressure is 12.5 gallons per minute. And if you were to take that information and fill in the worksheet, it might look something like this, though there is a mistake I need to point out. But here's our catchment container size. Here is the desired sprinkler operating pressure of 30, our elevation change. It even shows you here what the calculation for determining pressure loss due to elevation is going to be. Now, this is the mistake I need to point out. They have mistakenly put in 30 here instead of 8, but it should be 8 feet times 0.433 psi per foot. It gives you a pressure loss of 3.46. Then the pressure required at the gauge, we take the 30 psi that's given to us, divide it by the 0.67, and we subtract the pressure loss in elevation. So the pressure required at the gauge is 48.24, and you would adjust the valve until you got that pressure reading on the gauge. 24 seconds was given to us, and then finally that last calculation. So 5 gallons times 60 seconds in a minute divided by 24 seconds, and we end up with 12.5 GPM. Now you might also have the situation where you're starting with a design capacity. And maybe you've determined that based on an assumed flow calculation like we went over in the last lecture, or maybe you've got a pre-established zone or circuit size that you have to work with. So in that case, you're going to need a few pieces of information. You're going to need the time needed to fill the catchment device or bucket at the desired flow rate. You're probably going to still use a flow test apparatus and then adjust the valve until the desired flow rate is achieved. And then flow at the desired design capacity and pressure reading are going to be equal to the dynamic pressure available at the point of connection. And this method accounts for all pressure losses and changes due to elevation change through the system, pipe, valves, and other components that you may not know about. So as an example, let's go through this one. Let's say you have a desired design capacity of 20 gallons per minute. The elevation change from the point of connection is 13 feet. Catchment size is 10 gallons. And then as we adjust the flow rate to 20 GPM, the pressure gauge reads 58 psi. So the question is then, what is the design capacity? So we have some pieces of information given to us, namely the container size, the desired design capacity, elevation changes, but we still need to calculate pressure changes due to elevation. We still need to calculate the time it's going to take approximately in seconds to fill the container. And then we're going to determine what the pressure is when those times match. And finally, the sprinkler pressure available at the worst case head on the system. So the first calculation, again, it's the same as we've been doing. 13 feet in elevation change times our constant leaves us with a pressure change of 5.63 psi. The bucket fill time will be determined with this calculation. So 10-gallon container times 60 seconds in a minute divided by 20 GPM, which is our desired design capacity, leaves us with a 30-second fill time approximately. So if you were to do this in practice, you'd then perform a flow test and adjust the valve until the bucket filled up in 30 seconds. And you'd make those adjustments until it worked. And in this case, let's pretend we've done that. And the pressure that has to be on the gauge is 58 psi. Now in the final calculation, that 58 psi pressure is taken and multiplied by the constant of 0.67, and then the elevation component is taken into account as well and subtracted, and we end up with a pressure available at the worst case head of 33.2 psi. So if the worksheet were filled in, it would look something like this. Once again, there's a mistake here, but that elevation should be 13 feet times 0.433. But we end up with the pressure available at the worst case head of 33.2. So So in summary, these field flow tests can be used to determine system design capacity and dynamic pressure at the point of connection when you can't accurately calculate pressure losses. Additions to existing irrigation systems, maybe establishing a point of connection in a system where the water source is unknown, or when you don't know all of the system components that may exist. Those are situations in which you can use design capacity and available pressure calculations to get yourself answers on what you have available to you for your particular design.